My greetings to Doctor. We are from Group 3. Our group is consists of Zulaikha, Sharul, myself Naveen, and my Sara. So our presentation will be on experiment 6, which is torsion of bell. So the first part of experiment, abstract. The experiment was conducted to investigate the relationship between torque and the angle of twist of a circular cross-section specimen. The aluminum rod will be clamped in position with load applied. The rotation scale was set up 400 millimeters. The pointer on the rotation scale is set to 0 degrees of twist. The rod is loaded by securing it to the hanger. Finally, for each loading, read and record the twist of angle. The experiment was continued by changing the rotation from 400 millimeters to 200 millimeters. The diameter of the rod must be measured and registered. The relationship between torque T and the angle of twist of a circular cross-section specimen is directly proportional to each other, and twist is also proportional to the length of the shift L based on the result we obtain. The measured modulus of rigidity of aluminium, steel rod and nylon are 15,025.86, 35,520.16 and 15,645.07 respectively. The difference to their theoretical value are 42.6%, 55.04%, 79.14% respectively. The obtained modulus of rigidity was compared to the theoretical value in order to determine the validity of the torque formula and to identify any potential experiment errors. As a result, precaution steps were recommended to increase the experiment's accuracy. According to the experiment, it does not agree with the torque formula. This is due to the huge difference in the theoretical and experimental value.
Assalamualaikum and good day. My name is Sara and I will be continuing the presentation on the introduction, objective and also the theory. Okay, first, let's move right along with the introduction. Okay, what is torsion? Torsion is basically a type of deformation, which the definition of torsion is a twisting of an object due to the applied torque or due to a moment that acting on the object's longitudinal axis. Okay, so what is longitudinal axis? The axis is, for example, we have a pen right here. The axis will act or running lengthwise. That means that the axis is going in this direction, which means it's going from this end to this end through the center of this pen or through the center of the bar or a shaft or a specimen or a rod. And that's what it means by longitudinal axis. A moment which tends to cause the rotation or twisting is, we call it as torque. Torsion will generate stress and strain inside or within the member or the shaft. Therefore, we can analyze torsion by calculating the stress and strain it created within the member. And this moment have the same magnitude but opposite direction. Okay, what does this mean by this statement is, for example, we have a pen right here. We consider it as a shaft, and we have a moment that are acting on both ends of this bar or this pen. And the moment that acting here is going on this direction, and the moment that is acting on the other end is going in this direction, which means it's going to the opposite direction with each other. And that's what it means by this statement right here. Therefore, this moment or torque, we can consider it as a vector, or it is a vector quantity and can be represented by a curved arrow or a couple vector. There are plenty of objects that is being subjected in torsion to torsion in the engineering application. For example, the most common one is the transmission shaft, which uses rotation to transmit power from one location to another location. Another example is the shaft that is being used to transmit power from the blades of a a wind turbine to its generator. And also this shaft can be hollow or solid. And as for the objective of this experiment, the first one is to investigate the relationship between torque and the angle of twist theta of a circular cross-sectional area of a specimen. And the second one is to determine the modulus of rigidity with the symbol G of materials. Okay, now moving on to the theory. When the bar is subjected to torsion, it can be imagined that the bar is made up of multiple individual discs that rotates relative to one another when the torque is being applied. So what does this statement mean? For example, we have a bar right here. We can imagine that this bar have individual cross-section, and this cross-section have multiple round discs or individual discs. So when this bar is subjected to torsion, these individual discs will rotate relative to each other and they will not deform. And this statement is true only when the bar have circular cross-section. And therefore, the distribution of shear strengths that were created by torsion within the circular shaft can be determined. And furthermore, this will show that the shearing strain, gamma, varies linearly with the distance from the center of the cross-section. The changes in the angles created by both sides of the shaft can be measured and calculated to obtain the shear stress by using this formula. Gamma is equal to P theta divided by L, where gamma is the shearing strain, P is the length from the center to any point of the shaft. Theta is the angle of twist and L is the length of the shaft. Shearing strain that occur at the surface of the shaft is the maximum shearing strain. And we can substitute or we can replace P with C, which is C is the radius of the shaft. And as we can see here on the figure, L is the length of the shaft and gamma max is the maximum shearing strain which occur at the surface of the shaft, and C is the radius of the shaft, and theta is the angle of twist. And therefore, the angle of twist theta and the maximum shearing strain are related as follows. Gamma max is equal to C theta divided by L, where theta is the angle of twist and L is the length of the shaft. In elastic range, the shearing strain and shear tau is related by applying the Hooke's law because the stress produced is not exerted anywhere within the shaft. And we can use the formula here, which is gamma max is equal to tau max divided by G, which also equal to Tc divided by Jg. Solving for the angle of twist theta, we can get Tc divided by Jg is equal to C theta divided by L. And therefore, we move C to the other side of the equation and it will cancel with each other. So what is left behind is theta is equal to TL divided by Jg, where theta is the angle of twist, T is the torque exerted on the shaft, L is the length of the shaft, J is the polar moment of inertia. Okay, so the definition of polar moment of inertia is basically cross-section's resistance toward the torsion deformation. And the equation is pi over 2 times C2 to the power of 4 minus C1 to the power of 4. This equation is actually tells us that the shaft is hollow. Because if the shaft is solid, we only have one radius. Therefore, the equation will be pi divided by 2 C to the power of 4. And lastly, the G, which is the modulus of rigidity. And I think that is all from me. Thank you.
Assalamualaikum and good day. My name is Zulaikha. So I'm going to discuss about the apparatus and also methodology used in experiment 6. Alright, so here we have torsion bar testing machine with loads. Yeah, okay, and we have 5 Newton and 1 Newton load. We also have ruler, vernier calipers, spanner, and some specimens like steel, aluminum alloy, and also nylon rod. We also have ball bearing in the housing here, and also hanger cord 75mm effective diameter of torsion head. Okay, so firstly, the aluminum alloy rod was clamped in position and load hanger was placed on a cord. The rotation scale was set up 400mm from the feed scale, from the feed clamp, and its pointer was fixed to 0 before we start steering. We need to make sure that our pointer is at 0 before we start our experiment. Okay. The twists of each experiment were recorded for every 5 Newton increments until it reached 40 Newton. Means like we need to record every twist of each specimen for every 5 Newton increment until we reach 40 Newton. Okay, then the load will remove. The position of rotation scale together with the pointer will change to over 200mm from the clamp. Then the above procedures were repeated. The diameter were measured and recorded by using vernier calipers. Then the specimen was changed to steel rod. After we used aluminum, we changed to steel rod, and the procedure was repeated from 400mm in length only. Finally, we changed to nylon rod. The nylon rod was clamped in position, and the twists for 200 and 400mm were measured when the load of 5 Newton by increment 1 Newton was applied to the torsion head. Then the load was removed and occurring a full elastic recovery were recorded.
Assalamualaikum and hello Dr. Arif. So my name is Sharul Reza. So today I will be presenting the result and a discussion for our experiment. For the result, Table 1 shows the data for aluminum alloy rod where the given diameter is 6.31mm. As you can see in Table 1, the load hanger is at 5 Newton increment until it reached 40 Newton. So the twists of each specimen were recorded for every 5 Newton. So after the angle of twist is recorded, we then calculate the torque for 400mm and 200mm. The torque is calculated using the formula T equals to R times F, where R is the torsion head effective diameter and F is the force or load added. For example, we calculate the torque for 400mm at 5 Newton, where the radius is 75/2 times with 5 Newton, and we got the value for torque is 187.5 Newton. So the calculation for torque is the same for all load and the same for 400mm and 200mm. So graph 1 below is graph of angle of twist against torque for aluminum alloy over 200mm and 400mm. So from the graph angle of twist versus T, the value of slope of graph can be determined, where the y-axis is the angle of twist in degree and the x-axis is the torque. And for 400mm, the value of slope is 0.0098. And for 200mm, the value of slope is 0.0049, which is half of 400mm. From the value of slope we got previously, we can calculate the modulus of rigidity of aluminum alloys. We can calculate the modulus of rigidity using the formula G is equal to L over mj, where J is polar moment of inertia and it is equal to pi/2 times width radius of rod in the power of 4. For the aluminum alloy rod, the diameter is 6.31, so we just insert the value to calculate the polar moment of inertia, and we got the J value is 155.638 millimeter. After we got the value for polar moment of inertia, we just substitute the value in the formula given, which is G is equal to length over slope times J. And for 400mm, the value of modulus of rigidity is 150 to 5.86 Newton, and for 200 millimeter, the value of G is 150 to 5.86 Newton. The value is the same because the slope for 200 millimeter is half of 400 millimeter. So the average value is the same since both value is the same. So table 2 is the data for steel rod, and the given diameter is 4.99 millimeter. Same as the previous table, the hanger load is at 5 Newton increment until it reaches 40 Newton. Then we calculate the twist of the rod in degree. After that, we calculate the torque, which is the T equal to R times F. The value of torque is the same as previous table since the radius and the load added is the same for both data table 1 and table 2. So for graph 2 below is the graph of angle of twist against torque for steel rod over 400 millimeter. So from the graph of angle of twist versus T, the value of slope can be determined. So for 400 millimeter, the value of slope is 0.0106. From the slope we got from previous graph, we can calculate the modulus of rigidity using the formula G is equal to L over mj, where the value of J, polar moment of inertia of steel rod, is 60.87 millimeter. From that, we just substitute the value for L, M, and J in the formula, and we got the modulus of rigidity of steel rod in 400 millimeter is G is equal to 355 to 0.16 Newton. So this is table 3, the data for nylon rod, and given diameter is 6.5 to 5 millimeter. The hanger load is at 1 Newton increment until it reach 5 Newton. Then we calculate the twist of the rod for 400 millimeter and 200 millimeter in radian. From that, we can calculate the value of torque, which is the same as previous. T is equal to R times F, where R is equal to 75 over 2, and F equal to 1 for hanger load 1 Newton and torque 400 millimeter. And we got the value for torque at 400 millimeter at 1 Newton is 75.5 Newton. So we just use this formula to calculate all the torque for 2, 3, 4, and 5 Newton. So graph 3 below is the graph of angle of twist against torque for nylon rod over 200 millimeter and 400 millimeter. So from the graph of angle of twist versus T, the value of slope can be determined, where the slope for 400 millimeter is 0.0069 and the slope for 200 millimeter is 0.0051. From the slope given, we can calculate the modulus of rigidity for nylon rod. The value of polar moment of inertia for nylon rod is 177.96 millimeter. From that, we just substitute the value for L, M, and J in modulus of rigidity formula, and we got the G for 400 millimeter is 18664.296 Newton, and for 200 millimeter is 12625.85 Newton. So the average value for both length is 15645.07 Newton. For the discussion, the first one, to what extent does the experiment verify the torque or twist formula based on the graph plotted? So angle of twist against torque. So based on the three graphs plotted, we can conclude that the angle of twist is directly proportional to the torque. As the angle of twist increase, the torque also increase. The length of the rod or material will affect the slope of the graph. As you can see in graph 1 and graph 3, when the length is decreased, it will cause the slope to be more steeper. So the graph also shows that the type of material will affect the angle of twist and exhibit their purely elastic behavior. From the graph, the modulus of rigidity is inversely proportional to angle of twist. A smaller angle of twist causing the value of modulus of rigidity increase. Hence, we can conclude that the angle of twist is directly proportional to torque, angle of twist is directly proportional to the length, and angle of twist is inversely proportional to modulus of rigidity. So therefore, we get the formula to calculate the modulus of rigidity, where angle of twist equal to TL over JG. Number 2, determine the modulus of rigidity of material. From the result and the calculation, the experimental value for modulus of rigidity for aluminium alloy is 150 to 5.86 Newton, and for steel rod, the experimental value is 355 to 0.16 Newton, and for nylon rod is 15645.07. To calculate the percentage error, we use the formula experimental times with theoretical over theoretical value and times with 100% to get the percentage error. The percentage error is quite high for the three material due to some error, where the aluminium alloy is 42.64%, and for steel rod is 55.04%, and for nylon rod is 79.14%. From the result, we got the value of rigidity G for aluminium rod is 15025.86 Newton, for steel rod is 3552.0.16 Newton, and for nylon rod is 15645.07 Newton. So the percentage error is 42.64%, 55.04%, and 79.14% respectively. Some of the value has huge difference from the theoretical value, probably due to some error. So steel has the highest value of modulus of rigidity and applied torque at failure, which means it is the strongest material from the available three material, so it can withstand higher shear stress than other two materials. Aluminium alloy comes second among the three materials, as it can bear more shear stress and applied torque than nylon, but cannot take as much as torque as steel can. It can take more angle of twist due to material property called ductility. So nylon rod has the least value of rigidity and shows nylon has the lowest ductility. So what is the source of error and how to overcome the error in this experiment? So the first one is experimental error. The rod may not be kept in good condition, causing the rod to be exposed to heat, making the temperature increase and causing the error in ductility. So to avoid this, the apparatus should be kept in the right place away from heat. Error number 2 is systematic error, where parallax in reading a meter scale when taking the angle of twist value. So to avoid this, our eyes must be perpendicular with the meter scale when taking the reading. And the last one is external error, which is windy environment or air movement in the lab can cause the weight to move, making the inaccuracy of taking the reading of meter scale, as the meter scale can stay in place when the weight is moving. So to avoid this, so make sure that the experiment conducted in closed space where there's no air movement or no windy environment. I think that's all from me. Thank you.
In conclusion, the experimental result indicates that the experimental values are varies with the theoretical value due to the error occurred in the experiment. Furthermore, it is found that the formula of torque is not satisfied due to the huge difference in the theoretical and experimental value. The greater the torque applied, the greater the material's angle of twist. The relationship between torque and twist of angle was investigated as a conclusion. The model of rigidity of the rods was determined as follows. For aluminium, it is 15,025.86. For steel is 35,520.16 and nylon is 15,645.07. That's all from us. Thank you.